So let's get started. Welcome you all to the class. So yesterday we looked at some review of Cartesian tensors, right? So I think many of you are familiar, some who are not. Let's hope that it was clear. So we looked at only the basic part of it. If you are interested in knowing more, there are books on Cartesian tensor calculus. We don't need all those things. So the basics, what is required, that you should know the summation rule, and you should be able to identify the free index, and if you want to change it, change the free index throughout, not for only one or two terms. Okay, that is the basics. So we look at we practice today one or two terms before we go into the governing equations. Okay, so we discussed one thing called so we are still at the theory part where we looked at Cartesian tensors, right? So we looked at what is called vorticity, right? So the omega in your vector form, which I told you is not so useful when we go into the world of turbulence, right? So this is written in tensor notation as omega I equal to your epsilon I j k dou u k by dou x j. Okay, so now let's see what is the vorticity component in the I equal to 1 direction. So let I be equal to 1, implying you are looking into the coordinate direction 1, right? Let's say x y z, then x is 1, let's say, or x1. So then omega 1 will be, I is the free index here, j and k are repeated, so it has to be summed over it 2 times. So let's write first epsilon 1 j k dou u k by dou x j. Okay, now we apply the summation rule once. Let's sum it over j first. So I get epsilon 1 k dou u k by dou x1 plus epsilon 1 2 k, we are summing over j, right? So it's dou u k by dou x2 plus epsilon 1 3 k dou u k by dou x3. Now it's readily seeable, we don't have to sum over the k for the first term, because we can readily see from the Levis-Civitaz epsilon has to take cyclic or anti-cyclic values. It should be 1 2 3 2 3 1 so on, or 3 1 2 and so on. It's 1 1, so it doesn't matter what k value takes here, since 1 is repeated, it will be 0 here, correct? So I don't need to, you can expand it and make it 0, but it is smart to just say this is anyway going to 0 here. So this term I don't have to expand, I'll only expand the other 2 terms to see, right? So this gives me now I expand or sum over. So here I have summed it over summation over j. Now I will do the summation over k, the Einstein summation. Okay, so I do now over k for both the terms, so I get epsilon 1 2 1 dou u1 by dou x2, I'll write it below for this, plus epsilon 1 2 2 dou u2 by dou x2 plus epsilon 1 2 3 dou u3 by dou x2. Again you see here this is 0, 1 to 1 is 0, 122 is also 0. Only one term remains. Now I expand the last term here, right? We are only expanding these two terms. So now I expand this third term, which is epsilon 131 dou u1 by dou x3 plus epsilon 132 dou u2 by dou x3 plus epsilon 133 dou u3 by dou x3. Okay. So again this is 0, this is 0, leaving out only two terms. So the final notation is basically your epsilon or omega 1 is essentially equal to omega 1 is equal to your epsilon 123 dou u3 by dou x2 plus epsilon 132 dou u2 by dou x3. Now what is the sign for this? 1, 2, 3 is positive, right? It's positive one, it is in the cyclic. 1, 3, 2, right, in the counterclockwise. So this is negative sign. So therefore we have omega 1 is equal to plus 1 dou u3 by dou x2 minus, I'll just say plus, sorry, so it's positive here, minus of dou u2 by dou x3. So you don't need to remember the sign here, right, unless you want to work with a vector form here. The Cartesian tensor rule itself will tell you, it's much easier. You don't have to remember the sign, whether it should be assigned negative or positive to the gradient. Similarly, you can expand to omega 2, omega 3 and so on. This is just a practice, so you need to get used to this, and as I said, we are mostly going to use this Einstein summation rule. Repeated indices, you have to sum it over that particular index, okay, and sometimes we use this free index rule to change an index throughout, that we do it. Fine. So with this we can go ahead and we are ready to start with our governing equations. And now when I talk about governing equations, that means the governing equations for turbulent flows. Obviously the Navier Stokes, as I said, knows about turbulence. It knows about laminar, transitional, turbulent flows. It knows about everything, right? But the equation is not revealing to us what is the origin of turbulence, which term knows about turbulence, that we don't know. Everything is concealed inside Navier Stokes, right? So governing equations, you can take it as chapter 2 actually, this particular part. Let's call this chapter 2, governing equations. For what? Of fluid motion, right? And we are particularly interested in turbulent fluid motion, not the laminar. So note here is that the Navier Stokes equations Navier Stokes, a system of equations, constitutes 3. Many times I see that students think only the momentum equation is the Navier Stokes equation. It's a system of 3: conservation of mass, momentum, energy. Okay, so Navier Stokes system of equations knows about turbulence, but it is concealed. We don't know the origin of turbulence, right? So the question is origin of turbulence. which term knows about turbulence? For that, we use chapter 1 basics that we studied. That is, we looked at the statistical analysis. We know now if a quantity is given, we know how to split into its statistical component and the random component. The random is the turbulent. So we know the mean and the fluctuation. So we can now write equations for the mean fluid motion as well as the fluctuating fluid motion. That's what we are going to do now. Okay. So Navier Stokes system of equations now. So first we look into conservation of mass here. Conservation of mass. I will proceed only in terms of Cartesian tensor notations. Okay, leave out the vector form. So we write this as dou rho by dou t plus dou by dou x, let's say I or j, can use let's say j here, rho uj equal to 0. It could be I also, I or j or k, doesn't matter. So now the first term is of course similar to you in vector form also. The second one is what you would write it as in a divergence form. Okay, that I have not written. This is much more nice because the entire Cartesian tensor comes in the tensor calculus, and therefore it's readily applicable. The rules that you know in calculus, it's readily applicable here, right? So now I can easily apply the chain rule for products or product rule here for the second equation. So second term here, right? So I can apply, I can say applying product rule, or you may call it chain rule, whatever you are familiar with. If I do this, I get dou rho by dou t plus I get uj dou rho by dou xj plus rho dou uj by dou xj equal to 0. Now here, to proceed further in this entire course, I am going to take constant density, right? So this entire turbulence modeling course, I am going to go with constant density flows. Okay. So now consider rho equal to constant, or I can say density, which is rho equal to constant. If I do that, I get the first term will go away, rho is constant, right? So obviously this term goes away for rho equal to constant. The second term also goes away for rho equal to constant. Only I get the last term, which is your dou uj by dou xj equal to 0, which is what you call a continuity equation in incompressible flow, right? Continuity equation in incompressible flow. So whenever I mention constant density, it obviously implies incompressible flow. Okay, so I don't have to explicitly say that again. Constant density will imply incompressible flow. So this is our equation for continuity that you already know. Even now we have not looked into turbulence and mean motion. It is still Navier Stokes system of equations. So now we go to the momentum equation, conservation of momentum. So before that we can expand this particular term dou uj by dou xj, right? So okay, so I have dou uj by dou xj equal to 0. So what should I do now when I see two repeated indices? Einstein summation, right? Einstein summation over j repeated twice. So what do I get? It's dou u1 by dou x1 plus dou u2 by dou x2 plus dou u3 by dou x3 equal to 0. So I have only one equation here, right? But I have three unknowns. So equation unknowns. I have one equation for continuity. I have three unknowns here, right? u1, u2, u3 are three unknowns. u1, comma, u2 and u3. For that, I can use conservation of momentum, which will give me three equations for the velocities, right? So I don't have to worry here. Otherwise, it's a problem. I have one equation, three unknowns means you cannot solve the equation. Luckily, we have conservation of momentum for three more equations. So we take conservation of momentum. Okay. So we have dou rho ui by dou t plus dou rho ui uj by dou xj equal to minus dou p by dou xi plus dou tau ij by dou xj. We already discussed the gradient term, how it has to be written in Cartesian tensor notation, how the divergence term is written, how the Laplacian, all these terms we discussed in the previously, right? So I have written the conservation of momentum in Cartesian tensor notation, and I already said rho is constant density, which implies incompressible flows. So I have dou ui by dou t plus, now I can use product rule again here. If I use product rule again, I will get ui uj dou ui by dou xj plus ui dou uj by dou xj equal to, I am taking the rho to the right hand side, I get minus 1 by rho dou p by dou xi plus 1 by rho dou tau ij by dou xj. I am taking the non-conservative form of the equation, right? Those who are familiar with fluid mechanics would know that this particular second term, the nonlinear or advection term, I have written in the non-conservative form. If you are using finite volume method, retain the conservative form while solving this. If you are using finite difference methods, this is fine, you can do non-conservative method. Okay. So now I have the equation here. So it's readily seen that any term here which will go away to 0 for constant density. This particular term, the third term on the left hand side, it's dou uj by dou xj, right? So this is this particular term, right? So this goes to 0. Therefore, I have a much smaller form of the equation here. Okay, so let's call this equation 1 here, the continuity equation, and then the momentum equation, equation 2 here. Okay,